Einstein's miraculous insight on time. Does his twin's clock dangle or dingle? My name is Johan Prince, and I invite you to accompany me on a juggernaut journey in time. Einstein's interpretation of the Lorentz coordinate transformation in terms of his special theory of relativity caused a paradigm shift in 1905 that still reverberates throughout modern physics. He claimed that these equations must replace those of the Galilean relativistic coordinate transformation by boldly assuming that time itself is a relativistic coordinate, which can therefore not be an invariant physics parameter that is the same within all inertial reference frames. Let us assume that Einstein had an identical twin, and that these are photographs of Einstein and his twin when they were about 25 years old. Assume further that at that age Einstein and his twin bought two perfect clocks, neither of which loses or gains time, and synchronized their clocks to both read zero just before his twin departed on a space journey at nearly the speed of light that lasted 50 years. According to Einstein's interpretation of time, it is expected that he and his twin should, after his twin's return, compare as follows. Let us assume that during this trip, Einstein thinks about his twin at an instant in time on his perfect clock. Does his twin coexist with him at that same instant in time? It seems logical to conclude that Einstein and his twin must coexist at all instants in time on Einstein's clock, since they are both at each instant present within the same universe. Now assume that an event occurs in the spaceship at a time t prime on the twin's perfect clock, and another event occurs at Einstein's position on his perfect clock. Can these events be simultaneous? To try and answer this, one must know what the word simultaneous means. According to all dictionaries, it means occurring or happening at the same time. Furthermore, the word coexistent is a synonym for simultaneous. In terms of this meaning of simultaneous, Einstein and his twin must coexist simultaneously at every instant in time on Einstein's clock, and they must also coexist simultaneously at every instant in time on his twin's clock. Can his twin coexist simultaneously with Einstein at fewer instances in time than Einstein simultaneously coexists with his twin? In terms of the meanings of simultaneous and coexistence found in dictionaries, one expects that they must simultaneously coexist for the same number of instances in time during the whole trip. If this is so, Einstein and his twin will be the same age when his twin returns to Earth. This must mean that an event at the time t prime on the spaceship can only be simultaneous with the event at time t, measured at Einstein's position, when the time on the perfect clock within the spaceship and the time on Einstein's perfect clock are exactly the same time t equals to t prime. Einstein, however, claimed in 1905 that simultaneous means that these two times can be different times. Since 1905, all mainstream theoretical physicists have accepted that the dictionaries must be wrong and that Einstein is correct. most modern theories of physics, from Einstein's theory of gravity, Dirac's wave equation for a single electron, quantum field theory, cosmology, particle physics, right up to the Higgs boson, are based on this miraculous interpretation of time by Einstein, notwithstanding the fact that the word simultaneous has always meant nothing else but the same time. There have been physicists who do not agree with Einstein's concept of simultaneous different times, since, as already pointed out, this is, according to the meaning of simultaneous, a contradiction in terms. Mainstream physicists who accept Einstein's interpretation have, however, argued for more than 100 years that experimental evidence proves that Einstein is correct, and therefore we must not allow our preconceived ideas derived from dictionaries to prevent us from accepting what is experimentally measured. The latter argument is seductively correct, provided that the experimental data is not misinterpreted, as had happened many times in physics, and provided that other possible interpretations are not repressed and censored, as had also happened many times in physics. The actual fact is that, to date, not a single clear-cut experiment has been done where a perfect clock had moved away at a high linear speed through gravity-free space and was then compared to another perfect clock that stayed behind. Only curved motion could be measured. Other physics effects owing to the latter motion had to be guessed and subtracted in order to reach the conclusion that Einstein's concept of time dilation on a linearly moving clock is valid. This raises many concerns which, in the interest of the future of physics, should not be ignored by sweeping them under the carpet. Probably the best known scientist who questioned Einstein's concept of time has been the distinguished British astrophysicist Herbert Dingle. Initially, he did not disagree with Einstein. He propagated Einstein's theories by writing an essay in 1922 entitled Relativity for All, followed by a book in 1940 entitled The Special Theory of Relativity. It has been reported that Einstein valued this book very highly. It was only during the 1950s that Dingle became convinced that Einstein's concept of time must be inconsistent with reality. He asked a simple question. If two synchronized clocks move with a speed v relative to one another, which clock is stationary and which clock is moving relative to the other clock? The obvious implication is that if there is no criterion to decide this, then both clocks must keep the same time, as is demanded by the meaning of simultaneity that is found in dictionaries. This question has never been answered from the time that Dingle asked it 60 years ago. Instead, all hell broke loose around Dingle's head. The attitude was and still is that only a fool and a crackpot who never understood the special theory of relativity would dare to ask such a stupid question, which therefore need not be answered. Dingle very quickly found himself censored from publishing in peer-reviewed journals. In exasperation, he ended up writing a book which was published in 1972, 6 years before his death in 1978, entitled The Science at the Crossroads. In 2008, Professor Ian McCausland a renowned professor at Toronto University, summarized this controversy as follows. On one thing, Professor Dingell's critics are all agreed, that he is wrong. They do not all agree, however, on the nature of his error. Some give arguments which are no more than illustrations of the obvious fact that the reciprocal Lorentz transformation is algebraically consistent. Some claim that the problem requires the general theory of relativity, and some appear to regard the matter as settled by their knowledge of four-dimensional space-time. Some argue with patience, while others thinly disguise their irritation. The incontrovertible fact remains that to date there has still been no direct answer given to Dingell's question by anybody. His critics avoided and still avoid this question like the plague. No matter what one wants to believe about the physics involved, the manner in which Dingell was stonewalled on this question is a disgrace in the field of physics, comparable to the way in which Galileo was treated by his peers during the 17th century. This raises a question. Is it possible to find objective evidence or logic which can discern who and what is correct? Are Einstein's simultaneous different times correct, or Dingell's argument that two different times cannot be simultaneous? Let us revisit the standard method used to derive the Lorentz transformation. This will be done in two ways. In the first case, Einstein's assumption that the time within one inertial reference frame is simultaneously different from the time within the other reference frame will be used. And in the second case, Dingell's assumption that the time obtained from the Lorentz coordinate transformations are not simultaneous will be used. In this slide, the red reference frame K is chosen to be stationary. With this choice, the origin O' of the yellow reference frame K' is moving with a speed v away from the origin O of K along the x-axis of K. It is assumed that there are two perfect clocks at O and O', which are synchronized to read that t is equal to t prime is equal to 0 when these origins coincide. The assumption is then made that a point-sized light source emits a spherical wavefront from the coincident position of O and O' at the time t equals t prime equals 0. Since, as Einstein deduced from Galileo's principle of relativity, the speed of light must be simultaneously the same within K and K', this spherical wavefront must move away in all directions from O' with the speed c within K', and must simultaneously also move away in all directions from O with the same speed c within K. The same wavefront, shown simultaneously by the yellow circle O' and the dashed red circle around O, will not coincide within itself in space if it were possible to view it simultaneously from the origins O' and O. The situation is shown when the time at O' has increased to be equal to t'. Since the times at O' and O were chosen to be equal to 0 when these origins coincided, this means that O' must have moved a distance vt' from O, and that the spherical wavefront around O' must have a radius of c times t', where c is the speed of light. Although the same spherical wavefront around O, dashed red circle, is shown to have the same radius as the radius of the same wavefront around O prime, solid yellow circle, this cannot be the case if Einstein is correct that the time t at O is simultaneously different from the time t prime at O prime. Subject to this possibility, we do not yet know what the radius ct around O must be, since we must first find a rule from which we can derive what the simultaneous different time t at O must be when the time is t prime at O prime. Following Einstein's cue, the derivation of the equations of the Lorentz coordinate transformation that gives a different time t at O when transforming the time t prime at O is done as follows. The equations for the spheres around O and O prime are written down by arranging the terms so that each expression is equal to 0. It is then claimed that the required rule to obtain the time t at O from the time t prime at O prime is given by a template equation which is obtained by setting these two zero expressions equal to one another. This means that 0 is set equal to 0. It is well known in mathematics that in most cases such a relationship leads to an undetermined result in the same manner as dividing by 0 does. This can be seen as follows. If this equation can serve as a template rule from which one can derive the Lorentz coordinate transformation of time, it must define a definite rule from which a one-to-one relationship is defined from a specific point with coordinates x prime, y prime, z prime at a specific time t prime within k prime into another position point also with unique specific coordinates x, y, z at a unique specific time t within k. But this template does not give such a one-to-one rule. It only relates a specific point x prime, y prime, z prime at a specific time t prime on the wavefront around O prime to any point x, y, z on any wavefront with any radius c times t around O, where t can have any value from 0 to infinity for the time at O. Thus, this equation is not sufficient to determine a unique rule from which the Lorentz transformation for time can be derived. Additional information is required. It is suspected that Einstein knew beforehand what the Lorentz equations are, which he wanted to derive, and he thus also knew that before and after such a transformation one must have that y prime is equal to y and z prime is equal to z. He thus proceeded to choose that y prime is equal to y and z prime is equal to z, even though his template equation does not demand that this must be so. By using this foresight, which he should not have had, and did not admit that he had, he obtained a two-dimensional position-time equation which, however, still suffered from the fact that for a specific choice for x prime and t prime, this template equation does not define a unique one-to-one relationship to definite values of x and t. It is still indeterminate. In order to rectify this situation, a new guiding principle was unwittingly established by Einstein in 1905, which separated 20th century modern theoretical physics from classical theoretical physics. This new guiding principle is the following. fudge the mathematics. The fudge factor that has since been used to obtain the Lorentz equations from the indeterminate and template equation is the imaginary number I, which is equal to the square root of minus 1. It is assumed that time is not a real physics parameter, but must be multiplied by the imaginary number I to become an imaginary time. It is then argued that this changes the template equation so that it defines a coordinate transformation given by a rotation from a real x prime position and an imaginary I t prime into another real x position and an imaginary time I t. Since a rotation in real space of two real coordinate axes always gives a one-to-one relationship, it is argued that it must also be the case when choosing time as an imaginary coordinate. Amazingly, by doing this, the Lorentz equations magically appear, but not as functions of imaginary time. One would have expected that those coordinate transformations should only be valid for imaginary time, since the rotation matrix used for the transformation is only valid for imaginary time, not for real time. Furthermore, when one writes these Lorentz equations in matrix format using real time, the transformation matrix is not a rotation matrix at all. In fact, it cannot be a rotation matrix, since the rotation matrix is only valid around a single origin, not between two different origins O prime and O, which is the physically real situation for the Lorentz transformation. Why would the physically valid rule, which must determine the Lorentz equations for real time, have anything to do with imaginary time? I've never encountered a clock that measures imaginary time. Einstein's derivation of the Lorentz equations would have been far more convincing if he had chosen specific coordinates x prime, y prime, z prime at the real time t prime on the wavefront with radius ct prime around O prime, and then found the actual rule within real space and real time which determines the actual correct coordinates x, y, z at the actual real time t on the wavefront with radius ct around O. In order to try and find the latter non-imaginary rule, let us return to the spherical wavefront yellow solid circle around O prime at the time t. Since we do not know what the simultaneous size of the wavefront dashed red circle within K is, we leave it out of the diagram. Now choose an event that occurs at a specific position x prime, y prime, z prime on the wavefront in K prime at the specific time t prime. Since both y prime and z prime are perpendicular to the direction in which the relative motion occurs, one can replace them with a single radial parameter rho prime, as determined by the theory of Pythagoras. Since we know that this specific event occurs on the wavefront around O prime at time t prime, we can also leave this wavefront out of the next slide. If, as assumed by Einstein, the time is simultaneously a different time t within K, and that the event must be simultaneously on a wavefront with radius ct around O, then the radial distance of the event from O within the stationary reference frame K must be given by ct as shown. A template equation for a one-to-one transformation from x prime t prime into xt can now be obtained without equating 0 to 0, but by invoking the theorem of Pythagoras. This is possible since x prime ct prime and rho prime form a right triangle, and x, ct and rho prime also form a right triangle. Since these two right triangles have the same length rho prime in common, the two sides of the template equation are now not uniquely zero as Einstein had assumed, but both are equal to rho prime squared, which need not be zero. Therefore, it does now define a unique one-to-one transformation which is determined in each case by the value of rho prime. If imaginary time is involved, it is now possible to argue that notwithstanding Einstein's mathematical clumsiness, all seems to have turned out to be honky-dory. However, according to this derivation of the template equation, the x position of the event as measured from O within the reference frame K is given by the expression x prime plus vt prime, which is the result that one expects from the Galilean transformation, not from the Lorentz transformation. According to the Lorentz equations, the coordinate x of the event from O is given by the Galilean expression x prime plus vt prime divided by a square root expression in order to obtain the x position of the event relative to the origin O of K. So which one of these two expressions is the correct x coordinate for the event? The Galilean expression or the Lorentz expression? If one still wants to assume against all odds that t prime and t are simultaneous times, this can only be so if the Galilean transformation and the Lorentz transformation are simultaneously correct. If this unlikely possibility could be the case, one should be able to get the Lorentz expression for x and t by combining this Galilean expression with a template equation. To keep the derivation simple, we will choose x prime to be 0. One then obtains a relationship between t and t prime in which the time t must be divided by a square root factor. This factor is, however, not the same as the square root which is valid for the Lorentz equations. It contains a plus, not a minus. This is powerful evidence that Einstein's concept of different simultaneous times is not self-consistent with the Lorentz equations. Let us now assume that the time at O and O prime must always be simultaneously the same, just as Dingle has argued. At the time t prime at which the event occurs on the wavefront around O prime, the yellow solid circle, the same wavefront around O prime, the dashed circle, must now have the same radius c times t prime. Since this means that the time within the stationary inertial reference frame K is also everywhere given by t prime, the coordinates within K which coincide with the coordinates of the event within K prime at the time t prime are thus actually given by the Galilean transformation, for which x is equal to x prime plus vt prime, not by the Lorentz transformation. So why do the Lorentz equations give a different position x and a different times t within k for the coordinates of the event when it actually occurs within k at the position x equal to x prime plus vt prime at time t prime. A compelling explanation is that the Lorentz equations do not give the actual position value x equal to x prime plus vt prime at the actual time that an observer within k will measure when he/she is coincident with the event, but it gives a non-simultaneous position value at another non-simultaneous time t, which manifests for the event relative to a non-coincident observer at the origin O of k. The reason why the actual simultaneous position coordinates x prime plus vt prime cannot manifest at O at the actual time t prime for the event is that the same wavefront, as it manifests within the stationary reference frame k, is not coincident with the event at the time t prime at which the event occurs simultaneously within both k prime and k at the same instant in time t prime. The event can thus only be recorded at O when the wavefront coincides with the position coordinates x prime rho prime of the event within the inertial reference frame k prime as shown in the following slide. While this wavefront around O moves towards the coordinates x prime and rho prime, the origin O prime simultaneously moves further away from O, so that the coordinates x prime and rho prime within k prime also move away with a speed v from O. The wavefront around O chases these coordinates until it catches up with them at another time t than the time t prime at which the event actually occurs at the coincident coordinate x equal x prime plus vt prime. Only now, at another non-simultaneous time t, is the distance of the position coordinates x prime and rho prime, which are stationary within k prime, a distance ct from the origin O of k. And only now can this time be recorded at O. One can, however, still obtain the same template equation that Einstein had obtained fortuitously by equating 0 to 0. This can still be done by using the theorem of Pythagoras, even though t prime and t are now two different non-simultaneous times. This is so since x prime ct prime rho prime as well as x ct rho prime still form two right triangles with equal distances rho prime. The coincident x coordinate when the wavefront around O reaches the coordinates x prime p prime rho prime at the event within k prime at a later non-simultaneous time t are now given again by the Galilean transformation as x is equal to x prime plus v times t. Note that although this is still the Galilean transformation, it is the transformation at a different time t than the time t prime. By combining the template equation with this Galilean equation, x equal to x prime plus vt, at the different non-simultaneous time t, the Lorentz equations are obtained directly without having to fudge the derivation by invoking the imaginary number I. This is obviously a more logical derivation, since one does not have to assume the miracle that clocks exist which keep imaginary time. Therefore, when combining this Galilean expression x equal to x prime plus vt with a template equation and choosing x prime equals 0, one obtains the correct relationship between t and t prime as required by the Lorentz transformation. These times are thus not simultaneous times. This compellingly supports Dingle's assertion that the times t and t prime obtained from the Lorentz transformation cannot be simultaneous different times, but are different non-simultaneous times, and the synchronized perfect clocks at O and O prime must thus keep the same time ad infinitum. If I now claim that Einstein's twin brother returned from space, they will compare as follows. Would you believe me? If I, however, claim that after the return they will compare as follows, will you believe me now? If I ask you to vote which one of the following two gentlemen really deserve Time magazine's accolade as genius of the 20th century, which one will you choose? You be the judge. Dingle wrote the following perturbing message. It is ironical that in the very field in which science has claimed superiority to theology, for example in the abandoning of dogma and the granting of absolute freedom to criticism, the positions are now reversed. Science will not tolerate criticism of special relativity, while theology talks freely about the death of God, the religionless Christianity, and so on. The following letter from an editor proves that medieval censorship is back. Manuscripts which claim to disprove the theory of relativity or make claims that it needs to be modified due to internal errors in logic are not considered for publication in Physical Review letters. In our experience, such claims are without exception the result of misunderstandings of the theory on the author's part, mistakes in his or her calculation, or simply based on logical non sequiturs. The theory of relativity is one of the most experimentally verified theories in physics. The theory has been studied for a century now by several generations of scientists and mathematicians, and it is highly unlikely that someone will find an internal contradiction in it that has been overlooked by everyone else. Jeremy Malenfant, Senior Assistant Editor, Physical Review Letters. This attitude is treason against everything that physics is supposed to be. Nobody must be allowed to ever reject ideas in physics on the basis that it is highly unlikely that previous physicists could be wrong. This is a return to the dark ages of reasoning. The rot is unfortunately already so deep that it has become a total waste of time to read mainstream peer-reviewed journals like Physical Review Letters.